Okay, well that's good to know. So it looks like we've got a number of people here who came with good intent. I entitled the session Strange Bedfellows as a joke, and then I got to thinking about it. I could A, probably make a lot of jokes about it, or B, use it as a theme for talking about the presentation. But first, let me introduce myself. My name is Bill Jacobs. I've had a couple of roles at Revolution. I've been with Revolution Analytics for a couple of years, mostly doing product marketing, evangelism, and product planning. I came into the company after a stint in the big data and Hadoop business, so I've played the role also of CTO for our big data products and worked with the company to plan a lot of the work we've done over the last few years that have taken the R analytics language and enabled it to be used in an enterprise context on big problems that span 10, 20, 30, 50, or in some cases, 1,000-node Hadoop systems. And so about a year and a half ago, we began talking to Microsoft because we thought SQL Server and APS, or PDW in parenthesis, I don't believe that's its name now, could be very interesting additional deployment platforms. Our partnership actually went back further than that. A little bit later today, I'll show you a part of our tool chain, our IDE, which happens to be based on Visual Studio. And we actually partnered with Microsoft to build that. Microsoft actually funded a good part of it. So we've been working with Microsoft off and on for a long time. A lot's happening in the analytics business, and it came to the point where we knew we needed to take a major step up in order to stay at pace and continue leading in this very fast-moving space known as advanced analytics, predictive analytics, big data analytics, Internet of Things analytics, analytics everything. And so we were either faced with another round of investment to grow quickly, or with finding an appropriate partner with which to merge and join, and we chose to do the latter, and that company is Microsoft. I have a real pretty Microsoft blue badge here. I understand this is a pretty good thing. It's really good for a hotel discount, I found. It gets me into a lot of buildings. Had that about a week. So we're very new to Microsoft. We announced that we were intending to become part of Microsoft in January, and the actual closure of the deal has been occurring in steps and phases, and the rest, all about 80 of us, the entire company, became Microsoft employees just on Tuesday of this week. So I'm happy to be here. I hope you're happy we're here, and I hope that the next hour is useful for you to kind of lay a foundation of what we were doing and a little bit about what we think we're going to do working together with Microsoft. Before I go much further, I'd like to introduce one individual here, Marcello Bonatti. Why don't you stand up and wave your hand? Marcello is actually essentially my colleague on the Microsoft side of the business. He comes in with a lot of experience promoting Microsoft's big data platforms, particularly APS and PDW, and if I missed anything, now works for a fellow named Harain Oberoi in the product marketing organization, driving the entire advanced analytics messages forward for Microsoft. So Marcello and I will be hopefully able to answer any questions that you might bring up. There's too much tech here for me, but I'm going to do my best to manage all of this. If see smoke starting to come out, let me know, and I'll run for the door along with all these people over here who sat near it. The things that are driving our business and the things that are driving Microsoft's business turn out to be about the same. Everybody wants to talk about big data. Is everybody getting tired of that term? Yeah? Yell it out. You getting tired of that term? All right, well, we've invented some more to go along with it, so maybe we'll just distract the press away from using the term or something with Internet of Things or predictive analytics. But the fundamental reality is that data explosion is half of a problem, analytics is the other half, and the result is hopefully significant value. And analytics is the piece that we think enables the data explosion problem to turn from being a real pain in the butt and something that drives a lot of inches of ink over to something that actually becomes something you can tie to ROI. In order to do so, we have a problem. How many of you are card-carrying data scientists? Got a PhD in math or stats or been doing that for 20 years? There's a clue hiding in the fact that so many people are doing analytics and so few of you raised your hand. I work with a lot of those guys. I'm not one of them. My background's nuclear reactor design, and then 3 Mile Island happened, and I realized I was going to be working on a boat that didn't have any windows if I kept doing that gig. So I went in the computer business. But for the guys that work in the analytics business, the real card-carrying data scientists, the problems are twofold. One, the tools they learned on are becoming kind of old and tired. How many of you have SAS in your shop? How many of you love it? How many of you have SPSS and love it? SAS and SPSS are not going away. I'd love to say that poof, tomorrow we're going to take over their business. Won't happen, not in a million years. But the problems they solved historically do not lend them to solving those same problems in the future, and new solutions are required. Those new solutions bring with them the need for a new kind of talent. Fortunately, we're seeing a rapid upswing in the academic world of not only computer science and math programs and stats programs, but also business programs. I'm from Denver, Colorado. And the University of Colorado at Denver, or at Boulder, Colorado, in their business school, not in the math school, not in the stats school, in the business school, they have what is essentially a data science program. Their goal is to teach new business leaders how to build decision-making processes based on data rather than the historic approaches of my opinion is, my experience is. And so between about 40-50% of the math and science programs teaching this language called R, along with Python and Scala and some of the other emergent languages, and the business schools beginning to teach business leaders, new business leaders, how to think about data-driven decision-making, we're seeing academia begin to flood, not exactly flood, it's perhaps a trickle if you're looking for these people, but hopefully eventually a flood of new talent to help build the data science that's needed to turn big data, or data exhaust is my favorite term, into something useful to the organization. Finally, of course, we all know about the open source trend, and I won't purport to speak for Microsoft, but what we know about Microsoft is that many of the new leaders in the company, from the CEO on down, are largely being brought into the company from organizations where open source has been the foundation, like Amazon and Yahoo. And so the propensity of Microsoft to embrace open source has radically shifted, and very quickly. We are only one example of that. The combination of those three things, when married with a cloud computing future in the mobile-first, cloud-first vision of Microsoft's world, I think will answer a lot of challenges for you and create a lot of challenges for Marcello and I to build products that do it for you. Where do we fit in the stack of things? This is a diagram that Microsoft uses to depict kind of a layer cake. You know, we're in the tech business. We have to get it simple enough that marketers like me can talk to it. And this is the stack chart that Microsoft uses. In that middle layer, you'll see a bunch of different technology opportunities, technology possibilities. We fit essentially in the modeling layer and the machine learning layers on the right of that chart. The interesting thing is Microsoft has additional products that instantiate machine learning. The Azure and Azure Machine Learning products, the Azure ML Studio products, all provide a very strongly biased towards machine learning approach to transforming and analyzing data. Revolution Analytics provides somewhat a little bit more of a traditional statistics approach, and it has as much to do with time in market and age than anything else. But the combination of the two forms a very, very powerful capability for traditional statistics and bulky, absorb all the data, I have no beginning hypothesis kinds of analytics that you see today. How many of you use Netflix? How many of you know about the Netflix prize? Get after it, guys. It's like $1 million a year. Netflix uses a lot of advanced machine learning to decide how to present you new movies. And they do that with unsupervised machine learning types of techniques. And so the combination of these two are where we're going as part of Microsoft and where we were headed before. The real goal is this. How many of you have seen this chart before? I all went to the keynote. Okay, I can skip that one. Or can I? This is a very important chart because it depicts the difference between what a lot of people call analytics today and what we call advanced analytics. Today, analytics is an extension of BI to many types of companies. You can go to any BI tool and hear from them about their endeavors in the space called analytics. Where things begin to change is we start to talk about predictive analytics, where we're no longer looking at what happened, what is the aggregate number of customers who returned to our website, but instead began looking, of all the things we know about those that returned, what caused them to return? And therefore, what can I do to cause more of them to return? And then the final step in this chart, which I think is where we all want to go, is if we know what's worked in the past and we start to see change, we can then say the appropriate reaction to the change is some kind of a prescription for fixing a problem or for addressing additional skills, investment to the problems that one is solving, whether they are forensic study of stock trading patterns and looking for insider trading and the kinds of things the SEC does, or whether they are looking for an example I'll show you later, a genomics example. If I know my genes, I know what to tell my doctor to treat me for before I even show the symptoms. I'll show you an example of that later. So this is what we're about. This is what predictive analytics is about. As you cross from the light blue to the dark blue, though, most of the interesting problems become huge. Huge. How many of you go to a little bitty store named as Walmart? Oh, come on. I go there all the time. I don't like it, but I love it at the same time. Walmart runs clusters. Their research cluster alone in Silicon Valley is over 4,000 nodes. It is one of the credit card processing companies that has stood up 1,500 nodes in a single cluster on MapR Hadoop. I won't say what city they're in because that gives away who they are. But a lot of the problems that you can solve when you address the world as a predictive and prescriptive problem require the ingest of massive amounts of data. That'll come up again. So let's talk about this piece called R. How many of you have any familiarity with R? Okay, good numbers. How many of you know where it came from? How many of you could talk this chart? Here's the mic. I've been traveling for 4 out of 5 weeks. I'm a little road weary. R was actually originally known in the world as, well, it's an antecedent, a descendant of something called S+, which was an AT&T Bell Labs invented language targeted specifically to the task of statistics. It was commercial source. A couple of gentlemen in New Zealand didn't like that, so they set about writing an open source version, and that is now known today as R. About 2000, it was released as a publicly available open source language. A foundation was formed in order to promote it, and about 2007 or 2008, our company was founded to help make the language commercially usable and capable of gobbling up big data and dealing with the types of architectures that we have today for doing that. What is it? Well, it's a language, sure. Is that what's valuable about it? Nah. Kind of an interesting language. I don't find it particularly exciting, but then I'm a guy who used to program in Pascal, PL1, COBOL, a little bit of C, a dab of Java, and occasionally Python. It's just a language. What's valuable about R is that a number of years ago, thousands of data scientists began sharing their work and producing an increasing body of freely available algorithms, techniques, training, documents, connectors. You can go to the available community called CRAN and download connectors for your favorite genome sequencing machine. You can download probably 150 variants of one algorithm, linear regression. Now, sometimes it's a little bit daunting. There's so much there, and the community has ways of dealing with that. But beyond the language that is designed to make statistics and analytics very easy is this huge community and all of the accretion of work in this repository called CRAN. And so we're sort of on the razor's edge about R. What's the razor's edge? The razor's edge is we'd love to all break it so we could make it better. Make it automatically, implicitly parallel so we could push it into a PDW warehouse, to point at my colleague Marcello, who's had a lot of involvement with that, and have it just naturally run. And we could do that. However, nobody's figured out how to move R that far forward that fast without breaking compatibility with the 6,500 packages in CRAN that make it so valuable. And so R is moving at a reasonable pace forward, and at the same time garnering massive numbers of users. Our last estimates 2 years ago were 2.5 million users. So it's almost to the point of being called a phenomenon. This is a quick view. This is a little bit of an eye chart. I apologize. CRAN is the Comprehensive R Archive Network. That is a downloadable, mirrored site. There's about, 15 mirrors across the world. all the packages that have been written and contributed to R. And this is about 60% of what's available. There's another repository out there called Bioconductor that's used in the health sciences field that's pretty rich as well. You can look, if you can read some of the titles here, that some of this stuff is very general stats, and some of it is exceedingly specific. Genome sequencing, statistical process control, medical image analysis, psychometric models. Wow, I don't even know what those are. I have to go look those up. I'm a big user of Wikipedia these days. But this is actually the highest value point that has caused R to shoot essentially to the top of the charts as an analytics language. All the rest of these languages above it are general purpose. It is domain specific to statistics, and yet, even though it's domain specific, it's not used in general purpose computer science anywhere, still ranks number 9 in IEEE Spectrum's latest surveys. And we've been seeing this occur. So it gives some idea that not only is this the dominant language for use in analytics and statistics, but analytics and statistics are becoming a very important and widely used field. And I think the presence of all of you here is a little bit of a testament to that. But it's not perfect. R's got some limitations. It was developed in the 90s. It evolved to be very important in the 2000s. Guess what happened to 2000? What happened in computer architecture in 2000? What's that? Why did multi-threading happen? About 2000, Intel figured out that the width of a line on one of their chips was down to 10 atoms wide. And you can't make wires any narrower than about 6 or 8 atoms or they stop working. And so we went to multi-core, multi-threaded, multi-socket, multi-node architectures. Uh-oh, let's upset the apple cart. R was not written to run very well in those environments. It does okay if you use it to invoke something that does that, but R itself is single-threaded and works out of memory. This has been a limiter for R for a long time, and a lot of people come to us saying, okay, fine, we've learned about R, we've used it, but we've hit its limits. It does not allow one to run off of disk very easily. There are ways to do it. It does not allow one to parallelize a problem across 1,000 nodes of a Hadoop cluster very easily either. It also is an open source language without support. And so that is why Revolution Analytics was founded, and that's what we do. So let's talk about Revo, as we call it. Revolution Analytics, well, I'm going the wrong way. How'd that happen? Okay, we are a provider of support and enhanced versions of R, in a nutshell. Those enhanced versions accomplish a couple of things. We have some hardening capabilities and some increased math capabilities that we bundle with R, and we make it freely available. By the way, you can go to our website this afternoon and download our version of open source R that has increased math capabilities. It'll run on your laptop. I'm going to run some of it here for you in a minute. We deliver, though, scale, performance, and cross-platform capabilities by abstracting some of the algorithms, regression algorithms, clustering algorithms, decision tree builders, random forest decision tree builders, algorithms that throw out all the variables that don't matter and hang on to variables that do matter, feature reduction algorithms. And we make those run in parallel across all the threads, cores, sockets, and if you have a clustered machine, nodes of your system, so that you can gain all that horsepower but still call it from R. And then we provide commercial support, knowledge base. We support 100 and some odd user groups around North America. We put stuff back in open source. The first packages for Hadoop, called R Hadoop, were written by members of our team. They are in open source today. So we are doing everything we can to keep driving the R language further and further into prominence as the leading language for big data analytics. Look what I found. Is this going to work? Ooh. I like that. Well, it only works in one direction. There we go. So what do we do? Let's see if I got a slide ahead of myself here. Our vision has been all along that R will and is on the path to become the de facto language for math, stats, predictive analytics. Our mission is to make sure it does that in a way that is suitable to big data problems of the type encountered in enterprises today, and almost more importantly, that we know will be encountered as people begin to tackle problems like Internet of Things, sensor-based analytics. Anybody familiar or working in the field of IoT? How many of you don't know what IoT stands for? Okay, good. So it's sufficiently ubiquitous that either none of you are willing to admit it or only 3 of you don't. Internet of Things, IoT, is the notion that nearly everything that matters in the world is going to be connected. The data flows that we've seen in the emergence of the web era pale by comparison to the predictions from IoT. Once we begin connecting and extracting data from every automobile, every refrigerator, every widget, and by the way, the cost of the lump you put in something now to get it connected to the internet, it's about $2 factory cost. $2. Well, for $2, what could I do if I could engineer something that tracks my kid's backpack? Think about the problems you can solve, that sort of thing, but then look at the data flows and you see a 10x, roughly, prediction over the data flows that we're dealing with today. Go. Okay, so much for plan A. Let's try plan B. There we go. So what we do to solve this is simple. We produce software products starting with stable distributions of R. We test them a little thoroughly. We take the open source. We test it a little more thoroughly. We strip out the open source mathematics and we put in some Intel-based math that can achieve a 10x performance increase for very certain mathematical functions, but generally averages about a 2x performance increase. Makes a little better use, of course, threads and sockets designed for Intel architectures, and we redistribute that both in our free products and in our commercial. We then go about building a framework and a set of algorithms for the key functions that most big data analysts need to tackle. Regression, statistical tests, building a histogram in parallel in a Hadoop cluster, running a clustering algorithm that'll group people together in like behaviors. You could imagine if you're trying to build the Netflix, what movie, I'm trying to read your name, Ravi? Ruddy. If I were catching Roddy logging in, I would want to cluster him immediately with people who behave like Roddy so I could show him movies that I think he might like. The first step in that is either a clustering or a classifying algorithm of some kind. So we build that stuff so it can run in parallel. We then build deployment platform frameworks that those can drop onto so that when we build that clustering algorithm, we build it one time in C++, and that code can snap into a Windows machine. You'll see it here. Can snap into a Hadoop cluster and several machine architectures in between, so you can move your code around. You can pick the platform that you need. We support this stuff with commercial support programs. You can download our free version and go to a website and ask questions of the community, or you can buy a support contract and get the kind of 2-hour support or 4-hour support that you need to support stuff that's running in production and everything in between. We've been fairly successful. We're up to about 400 clients, everywhere from using a single workstation to putting things on a Teradata appliance or a big Hadoop cluster. And you'll see a lot of them here. This doesn't even begin to do justice to the customer base. But we can't go it alone. How many of you have heard the old saying that first part of any job is 80% ETL? 80% of the work is in getting the data. Guess what? I have bad news for you. That hasn't changed. And so a lot of our partners are either in the getting data business or displaying results business, and we go to market with them to help us. And then, of course, a lot of the solution providers on the far side of the chart are actually people who use what we do to build a service or a product they then sell. So let's talk about products for a minute. We have 2 products. We used to have 3, and one of them was just a services package, so we've simplified it down to 2 as part of our inclusion into Microsoft. The Revolution R Open product is all of open source R, works with everything in the repositories because it is open source R, but it has improved math capabilities, and we do a little more testing on it. You can go download it from our website today. The Enterprise product contains the big data scale capabilities, contains the ability, a gateway that will allow you to build an analytic script that generates a score or a graphic or scores an entire table of customers, and then hide that behind a web services API so you can make it callable from a business rules engine or a BI tool. Okay? A lot of capability in the Enterprise product we'll get into later. And then we offer these other services that I've mentioned. I won't dwell on this. This is kind of standard commercial software stuff. In our business, we're a little bit biased on one end of the scale about how our business breaks down. A lot of software companies, about 20% of their revenue and resources are dedicated to providing professional services. This is a new and nascent area, and so we're seeing a much higher number About 35 or 40% of our business revenue, time, people, everything is dedicated to providing services and training, helping people spin up and become capable of tackling bigger projects on their own. Let's see. Everybody wants to know, what can I do with it? What can I do with it? So let's have some fun. Over here, pick up. Somebody raise their hand and tell me what business you're in. No escape. Everybody's getting quiet. Okay. Equipment reliability for manufacturing or consumer products? Where? Okay. What's he got to do? He's got to take in all the potential factors that might cause reliability problems, take in a long history of how his products have performed, and if you've got 100 different factors going into that picture, can any human absorb that in their mind? Probably not. Or you can't mint enough of those humans that can figure out those patterns. And so one of the very common use cases that we see in predictive maintenance is, how do I keep everything on the manufacturing floor working without overspending on its predictive maintenance? The airline industry wants to know this because they want to track every landing, every operation of that jet engine, every time it hiccups, every time it hit a bird, and use all that information, plus the vibration they're measuring off the engine, plus the spectrographic content of wear metals in the oil, and pull all that together and decide, does this engine need maintenance? Good example. What's everybody else doing with analytics? Somebody else throw me an example. You guys are getting quiet on me. I'm going to have to get more animated. Go ahead. Healthcare. Tell me about what you're doing there. Okay, very good. Healthcare has been a very, very busy space for analytics. That's one. Another one of our partners, Accenture, are building healthcare fraud detection systems. What are they doing? They're modeling behavior among cohorts of consumers. And when they model that behavior, it establishes patterns of reasonable behavior. And if someone deviates outside the pattern, it trips a flag that says, review this transaction. So they can focus their fraud detection efforts on those things that lie outside of patterns. And we've got a number of examples of that in healthcare companies. And so what we're seeing is that there are use cases in nearly every industry of major business in America today. They're all different. Some of them will eventually become commercial products that you won't build yourself. But in absence of that, as we all know, if you don't have it, you build it if you need it badly enough. And that's kind of where the world is with advanced analytics. So Revolutionary Enterprise is the flagship product that most people use to do this. It's a big data analytics platform that starts with open source R and expands its capabilities to perform statistical and analytical computation, prediction in big environments, Teradata warehouses, Hadoop clusters, clusters of Linux and Windows servers. There are three things it does. Number one, it provides a lot of power because it harnesses the power of a lot of computational engines in parallel to do work. It also, because you're using the capabilities of a big cluster or a big server hooked to a large storage farm or a Hadoop cluster with 3, 4, 5, 10 terabytes per node, we have the ability to grapple with massive data sets in the product. And finally, platform independence is probably the most important of all. How many of you started analytics last week and expect to have finished next month? How many of you started in the computer business 20 years ago and you're still using something you built 10 years ago? That's the characteristic that we have to watch out for in analytics. It's a long-running science. This is a long movie. There's going to be a lot of intermissions. You don't know where the plot's going to lead. Hadoop is only essentially 3 or 4 years old, for example. How many revs of Hadoop have we seen go by that aren't perfectly compatible with each other? You want to make sure, whatever you're looking for, you look for something in which you can establish an environment, do work, and make sure that work's going to carry you forth to the future. And that's the third pillar of what we do with Revolutionary Enterprise. This is a platform depiction. Again, I told you we love our stack charts. So on the stack chart, and I apologize to those of you over here, our language interpreter that we use, called RevoR, is open source R. No more, no less. To change that would break compatibility with the 6,500 CRAN packages. Now, when I talk about 6,500 packages, I forgot to make one point. A package is not an algorithm. A package is a bundle of algorithms. There's one package in CRAN that has 800 algorithms in it, and there's 6,500 packages. I haven't bothered to count. I'd guess the number of available algorithms is somewhere in the 20 to 50,000 range. And by golly, we don't want to test them all. So we're going to stick with open source R until hell freezes over if we have to. But then we set about in this part of our product adding capability that makes it able to interact with very large data sets in parallel environments, the ability to build R scripts easily. I'll show you the IDE in a moment, and then put APIs on the front of those so that they can be integrated into automated applications, desktop information delivery stuff, business rules engines, automatic scoring of customer behavior every morning. We have one large account. You would recognize the name if I said it. It's a very short name. It's a Silicon Valley online commerce application. Can't say any more. However, 200 million clients. They want to run 30 scores per client every morning for 200 million clients. They could not do that with their current infrastructure until they pushed the work inside of their big data warehouses, and all of a sudden they got about a 500 to 1 performance increase because they were no longer hauling the data out into a file system somewhere to beat it up with their scoring tools. So this is the type of problem we're trying to solve. Taking this a little bit further, let's talk about the supercharging and how we accomplish that. So these are kind of conceptual diagrams. The goal of R is very simple. If you look at most R programmers, they're almost in a contest with each other to see who can write the shortest script, right? And one of the great things about R is it makes it easy. If you want to invert a matrix in R to do a correlation analysis of some kind, you want to invert a matrix. Who even knows what that calculation is? My father taught me. He's an economist. I forgot promptly. It's a good thing R came along because inverting a matrix in R is one command. Doing massive manipulation of two-dimensional matrices of data in R is part of what statistics guys do every day, so they wrote it into the language. That's great. So most of what goes on in R doesn't happen in R. It happens in the packages that our users call. The stuff from CRAN, the stuff from our product. And so historically, they've called these algorithms after loading data in memory with a single line call that says LM, linear regression, linear model. Build me a linear model that says the outcome I'm looking for is probably 0.2 times this variable minus 0.3 of this variable and crosses the 0 point here. Well, that's simple stuff. You can code that up in Java in about 15 minutes once you've got the 10 parameters. And that's exactly what people do in LM. The problem is traditional R did that in memory. And if the data is bigger than memory, you're a dead duck before you start. You try and load the data, and your steam flies out of the back of your laptop, and you're done. You're cooked. How do you solve that problem? Well, that's where we're going. Solve that problem by creating a new version of LM. Happens to be called in our product RX LinMod. Most of our algorithms, we just put RX on the front, indicating that they're capable of being remotely executed. What that does is allow me to say, well, you know, today I want to run this sucker on a whole bunch of data segments sitting out in a big storage frame and have the algorithm take a little bit of data in, work on it, throw it away. Take a little bit of data in, work on it, throw it away. Ooh, neat. Now someone using a Windows PC, as I'm going to show you on my massively powerful Surface, that I can eat data far larger than available memory. Once I've solved that problem, that's a parallelization problem. I have to rewrite the algorithm to get there, and we've done that work. Okay. I need a massively parallel battery for the clicker here. So we'll bag the clicker. So what we do is we rewrite the algorithms such that they make the work happen task at a time. And we write an initiator and a finalizer. And the initiator says, hey, every node, go out and grab a block of data and do your thing. And give me back the intermediate answer. Then it combines the intermediates, and it either gets a final answer, or it iterates, or it takes another step. But whatever happens, all this work is invoked by a single command. It conducts the same computation as LinMod did, but it does it by pushing the work into a bunch of little steps and combining it and acting on data a chunk at a time. So now we can tackle data that is 10, 100, or 1,000 times bigger than available RAM. The last step, which is actually the easier step, think about it. If I've got something that'll run across a bunch of threads and push work out into each thread and do data a chunk at a time, where no chunk knows about the other chunk, I don't have to go a whole lot further to make it work in Hadoop or in a large, massively parallel computation cluster or in an MPP database. And so the next step is let's build frameworks that allow us to live in Hadoop or something like that, where we simply distribute those tasks across all the nodes of the cluster. And so that's what our engineers did starting about 2 years ago and gave us the ability to run these algorithms, these These are kind of the hit parade of most used algorithms in big data. Everything from pulling in data in parallel, eating lots of data off a lot of storage devices, to doing things like what's the correlation matrix look like about the input variables and the output I'm watching, or predictive models that tell us what's going to happen next based on the history that has occurred so far, or based on what is known as a training set of data. Some of the more sophisticated algorithms on the right, stepwise regression, boosted decision trees, those kinds of things, are actually designed to help reduce the number of variables. How many of you know how many variables you could model on in your problem you're currently working on? 100? We have people with 10,000 columns in the table. How do you deal with that? Hey, you turn something loose that knows how to throw out all the stuff that isn't helping predict the outcome. Stepwise linear regression does a big linear regression and then starts chucking stuff out until it comes down to the 10 or 20 that are most influential in the desired outcome. And these are the more sophisticated kinds of algorithms. Each one of these has been rewritten in a parallel fashion and is made available through a single line call in R. The performance is dramatic. The blue line here is the open source generalized linear model. We measured this ourselves. And the red line is the remote execution parallelized version. Now, I haven't used its ability to run somewhere else. These are two tests run on a laptop. Because we use all the threading capability of the laptop instead of single thread, and because we bring the data in a chunk at a time, not only are we chewing up a lot more data for a given amount of time, but the blue line runs out of gas at about 300,000 events, ran out of 8 gig of RAM, 8 gig of RAM. The red line, since we're taking data in a chunk at a time, we can just keep right on going. It just takes a little more time. So this algorithm is 20, 30 times faster and capable of orders of magnitude more data running on a laptop. And these are the effects that begin to set us up for doing even more interesting things. This is the example that I mentioned a bit ago where the internet property company was trying to run about 20 scores in the morning on a couple 100 million of their clients, and the orange bar is how long it was taking to pull the data out of the data warehouse into a server, score the data, and then push the scores back. Pushing the scores back isn't very hard because that's just like 20, 30 columns versus 100 columns being hauled out. When you push the work inside the database, who cares how fast it runs? The movement of the data turns out to be the biggest problem. Anybody seeing this movement problem? You start tackling, I see a couple people nodding. Where have you seen it? Yeah. So I was visiting a large auto company in Detroit. That'll not make it too specific. That'll get it down to 3. And they said, here, run this thing, and they said, it takes us 6 hours to run this credit worthiness predictor. Cool, 6 hours. We can probably knock that down. We got it down to 14 minutes. And they came back and said, well, the 6 hours to 14 minutes was neat. But what really helped us was, before we could do the 6-hour run, it was taking 48 hours to haul the data out into the math server and put it back. So the combined effect of not moving data by pushing the work to the data instead of the data to the work, and the parallelization of the work across all the nodes in either the EDW or the Hadoop cluster or whatever, has these exceedingly dramatic benefits. So 5 hours here went down to just a few minutes, and in this case, it didn't even include some of the movement. So that's the first big benefit, is being able to act on big data. When we start looking at, I have slides out of order here. Okay, we start looking at making R capable of being deployed in the enterprise. Some of the questions come to, can I field something in my production environment that is not supported by somebody? How many of you have been involved with application development deployment? Are you allowed to deploy open source? How many? No? I heard a no. How many of you have a problem with open source and deployment into commercial uses? Lots and lots and lots of people have. Once they get something built, they say, well, who's going to answer the 1-800-IT-BROKE call? And if nobody's going to take the 1-800-IT-BROKE call, the governance bodies won't let them deploy it. That's fairly common. And so what we're attacking there is that even for reasonably simple uses of R, we provide validation, support, training, and services. So there's some place to go, so you don't have to rely on a midnight email back from a data scientist who works for the R Foundation in Austria when you have a problem. We offer a full set of courses and training called Academy R. Everything from, hey, I need to learn R, to I want to replace some SAS code with some R code. Or I want to do something massively parallel in Hadoop. We have a tailored set of courses to help you do that. The second part of making things, quote, safe for the enterprise is this integration problem. These are examples of various tools utilizing analytical computation that were done in R, but then posting that stuff and making it available inside of tools like Tableau or Power BI or others. All it takes is the ability to pull information in via web services, because we can expose through our gateways any of the R scripts via web services. And finally, as I mentioned, the thing you want to watch out for is building a consistent platform over time. It's really a neat idea to be able to write a script on a Windows machine, change one line of code, and says, run it in Hadoop now. That's great. Makes for a great demo, but that isn't the real problem. The real problem is, what's Hadoop 4 look like? Or how do you get to the cloud when you're on-prem? That's the real problem. If you're a CIO and you're making major investments in analytics, how do you get to the future without being tripped up by changes in something? How many of you are Hadoop users? Any Hadoop users? A few? Okay, Hadoop's great. It's powerful. It's a little raw around the edges. It's kind of like a snake. It can bite you if you're not watching, if you don't handle it right. It's very powerful. However, in addition to being powerful and a little bit rough around the edges, it's rapidly changing. Hadoop 1.0, MapReduce 1, came out, really hit the scene about 3.5 years ago. MapReduce 2 changed a whole lot of how it behaved and broke some people. And now people are even just 4 years into the life of MapReduce claiming that MapReduce is dead. Anybody know what the replacement is? Yell it out. Anybody using Spark? Okay. Spark is very likely to replace MapReduce. What will replace Spark and when? Probably within 2 years, something newer, better will come out. And so the rate of change of this platform is downright tumultuous. By building things so that we can deploy them on today's platform and tomorrow's platform, we allow the data scientists to keep working and move things to future platforms without the interruption that could cause a rewrite or recode of the application. So I'm going to run a quick demo for you. I'm not a regular user of the product, so if you will forgive me, I will show you the IDE and run a couple of things for you, but I won't go too deeply into it because I'm very likely to get the analytical equivalent of the blue screen of death by doing too much. So this is, I'm going to switch over here to the product, Revolution R Enterprise, and, well, maybe I will. And show you the product. So this is fairly traditional IDE, right? How many of you use Visual Studio? This is a little bit older revision of Visual Studio, and we plan to upgrade this in fairly short order. Our scripts look like anything else in an IDE with windows of code and browsers to take you through the hierarchical tree of source modules that have been built or included, with inspectors for looking into what packages have been loaded. So here's an example. These are available packages that are shipped with the product. They're actually out of open source, called base and recommended packages. It's about 800 statistical algorithms freely available, and the tool helps you bring those in and use them. And then hiding in here is, let's see, packages loaded, Revo Scale R. You'll recognize that as the name of those 80 or so algorithms that we've rewritten to act in massive parallel way, whether to grab all the threads in my laptop or to grab all the threads, cores, sockets, and nodes in an EDW. And those are visible in here. And then, of course, the Windows there's some other tools you can plug in. But what I wanted to show you is that when a typical user uses the R language, it's a command line tool. And so you type something into the command line, including an entire script, and say run, and it runs and you get an answer. It's not unlike how BASIC was in its original instantiation. How many BASIC programmers in the room? All right. How many statisticians here are armed and dangerous? Nobody raising your hands? Okay. The statisticians in the room blow steam out their ears when I say this, but you can think of R as essentially Visual Basic for stats. Its goal is to allow you to write as short a script as possible and link together as many things as you can get from somewhere else So you don't have to become a deep space R developer. And so in that guise, let's take a look at some data. Let's say that what I want to do is pull a file out of my hard drive. This particular file is called airline data, and it's a subset. It's I think 1,200,000 rows of airline departure and arrival data. It's about a tenth of a data set that's widely used in the industry for depicting data science. And so one of the things our IDE can do is just run whatever is highlighted or run the entire script. So I'll run those two things, and it says done. So it's associated my script with that data, identified the data set. Now let's go do some work on the data set. Perhaps we want to know a little bit about what's in the data set. So let's do an RX summary. And this is a command that's going to tell me a little bit about the data. And what it's going to tell me is things like there are 4 chunks of data in the set, right? Kind of big numbers. It read them in and chunked through them in tenths of a second per chunk. It then ran this RX summary command, which tells me a bunch of statistics about the data itself, what file it read, what the name was, where it was. Standard deviation, min and max for the arrival and departure times. These are very useful in planning how you're going to attack a data set. How many variables we actually had. It turns out there's only a few variables, but there are things like day of the week and arrival delay and those sorts of things. Now, if we want to then do some fun stuff like what's the delay pattern look like graphically, we can run that from within R. Histogram is a normal graphic technique, and if this works right, it's going to jump up with a histogram in a bit. Yeah, there's my histogram. Sure enough, airplanes don't generally arrive much earlier than when they were supposed to, but they oftentimes arrive later. That's the way you'd expect that histogram to look. And we chunked through, by the way, you can see right here that the histogram command read those, well, it says it read 460,000 rows in 2 seconds on that chunk. So the whole thing took about 5 seconds. So it gives you some idea of when you parallelize these kinds of calculations, you actually get some pretty sprightly behavior. I won't do the line plots. They run a little bit slower. So let's do a linear regression now. Why would I do a linear regression? Well, the most obvious reason I'd do a linear regression is to say is there something about the day of week, the time of the departure of the airport or the airline that I can say is more or less predictive of whether or not that flight's going to delay? Question mark. Answer. In just a very few seconds, I can pick through. Let's see what I went through here now. I'm already done, by the way. Here, the error value in the predictor that it built is an R squared of 0.82. It's pretty good. It tells me what are the modeling coefficients that it thinks I ought to model on, and basically any coder that knows his way around writing a model can take those numbers and go build the computation that says take this variable times this variable times this variable times a y-intercept of -3, and there's your prediction with an accuracy of that R squared 82%. Now, I'm not a statistician, and I know everybody in here who is probably cringing at the way I'm describing it. But the idea is that when I run an LM, a GLM, or a logistic model, what I'm basically creating is a mathematical predictor, or as we call it, a model. Okay? So a lot of what gets done here is creating models, validating models, creating classifiers that will look at an event and say, well, that's kind of like one of these. I'll model it with these guys. Or that's one of these, and I'll model it with these guys, and allow users to build up what would be called, well, we'll see a classifier being followed by a set of different regressions for each category of data, each one with its own particular equation. And by doing so, we can break up problem sets and get very high prediction in each one. The problem is, how do we do that fast? These allow us to do that in parallel. And as you can see, I was going through quite a lot of data in just fractions of a second. Some other examples here. Maybe I want to run a generalized linear model. And GLMs are basically regression models that have different data profiles or different data distributions that it's expecting. So the GLM computation on that data is a little bit more complicated. And you can see I've got down here in the bottom orange and busy, and it took me, what, about 3 seconds? Here is my intercept, standard error, and coefficients on the various parameters. and it took 2 iterations to build that GLM. This is actually an iterative algorithm. It'll actually go through it a couple of times trying to compute the best possible model. So that's what people do in R. Now, I don't have the tools set up here to show you, but if I built a model I liked, I have a whole host of options for how I instantiate the model. I can rerun the model every time by firing it up with a web services script. I can run the model every morning and score all my planned flights for the day and guess how many dollars I'm going to spend on hotel rooms for my passengers that get delayed by weather. I can take the model and export it out in a language called PMML, Predictive Model Markup Language. There are products out there that consume PMML and run inside of databases, Zemintus being the leading example. So there's a number of ways that we can then act on these models once we create them. But the primary goal is to create those. And now I want to bring up Joseph Soros.
You know, we are all big data.
Okay.
There are billions of letters of genomic data.
Okay, let's stand by
in every one of
get
our
the audio
cells.
up.
It turns out that each human genome is about 2 gigabytes of information. And with the power of R, we can analyze all of this data. And when we plot this set of information against the general population, we can actually see some incredible things about ourselves. So the first human genome was sequenced in the year 2000. It cost about $200 million and over 10 years of work. You know, since then, the cost of mapping the genome have come down much faster than Moore's law. It's about $1,000 to get your entire genome, and you can get the most important parts for about $100. And this is driving an untold revolution. In the future, when you go to a doctor, the first thing that they will do will be to map your genome to understand your disease risks. This will let them treat you based upon your individual genome, personalized medicine. You will even know the risks you should anticipate in the future and change your lifestyle because of it. So let's show that to you with a demo. Joining me is Mario, who was at Revolution Analytics. So genomes are analyzed using the language of R. It has one of the richest libraries for analyzing genomic data. 1,000 people worldwide have contributed their genome to scientific research. It is public data called the 1,000 Genomes dataset. It's about 2 gigabytes of data per person. And we're going to analyze all of that data and see their disease risks. And Mario is going to actually walk through the demo. Now, it's going to take only a little bit of code, but it's a tremendous amount of computation. So it really needs big Hadoop clusters. So if we could show the Hadoop clusters that we are actually showing, the slides, we're going to use about 8 HD Insight clusters in 4 Azure data centers. 2 in the US, 1 in Europe, and 1 in Southeast Asia, for a total of about 1,600 cores in the calculation. By the way, they are Linux clusters. We are actually running Revolution R on them, and Revolution R is going to coordinate the computation across those 1,600 cores in all of these regions across the world. We're actually going to take computation to where the data resides when we do that global computation. So now let's see the code. So only a few lines of R code. This is the code that's actually used to analyze the genomic data. It leverages some extremely powerful functions in an R package called bioconductor. And let's also see the code that coordinates the computation. So this is the piece of the code that coordinates computation on HD Insight clusters across 8 clusters across 4 data centers. Let's kick that run off, Mario. And let's see what it produces. It produces a heat map. This is a heat map of disease risks. Each row is an individual. We have fictitious names on the right, but each column is a disease. So let's take, for example, the second row from the top, Claire Hickman. Claire Hickman has a high risk of ulcerative colitis. And let's take, say, the third from the bottom, Sophie Albrecht. Well, it turns out Sophie has a high risk of multiple sclerosis. By the way, this heat map is an amazing visualization produced by a package called Shiny in R, and it lets you visualize things and zoom into these things. It's very, very powerful as well. So now you've seen the disease risks of a population, of the population we analyzed on the Hadoop cluster, and almost happens in a few minutes, and it's pretty amazing chunking through all of that data. Now, but what if we could take that R code, publish that as a web service API? So you saw me publish a web service API with Azure Machine Learning earlier. What if I could do the same and create an API that lets you submit data and see your disease risks? So let's see the scoring experiment. This is a scoring experiment in Azure ML. See that execute R script? That's where we can actually copy the R code and publish that as an API. So let's do that now. So Mario is going to copy some of the R code for scoring a person's genomic data, put that into the execute R script, and run that experiment. By the way, as it's running, execute R script shows you how easy it is to operationalize R. Any R code can be published as an API in the cloud. And Azure Machine Learning lets you do the same thing even with Python. It is the simplest, easiest way to operationalize your analytics code as APIs in the cloud. So now let's publish the web service, and let's get that API in the cloud. Here, that's the API page. You got the key. There's even sample code to call that API. But to test this, we actually created there's a sample code. If you click on it, you'll see C#, Python, and R code are automatically generated. So now, to call this API and show you the results, we created a mobile app. I'll tell you about that in a minute. Now, early in April, I sent a sample of my saliva to 23andme.com to sequence my genome. Last Friday, I got the results from that. And so for the first time, I was able to analyze my DNA and see my future. So let's do that now. So let's take the mobile app. Can you all see the mobile app? So I'm going to log into 23andMe, get the data from that website.
Can everybody read that? Your eyes are better than mine.
It's uploading the genomic profile. So you will see a graph that shows the risks. So the blue bar is the population risk, and red is mine. So you'll see that I have low risk for gallstones, low risk for asthma, certainly low risk for breast cancer. But let's look here at the top. Look at that very top line. That red bar shows 0.36. I have about 2.5 times the population risk for prostate cancer. And I just discovered that. That's my future predicted from my genomic data, R, and big data analysis. That's the power of big data and advanced analytics. So if we switch back to the slide, big data and advanced analytics can change lives.
Now let me tell you what you saw there. First of all, that was Joseph Soros. Joseph runs the Advanced Analytics product line for Microsoft, including engineering. He is the organization into which Revolution Analytics is aligned at the moment. He also owns Azure Machine Learning and a few other related technologies. That demo was built using a combination of two things, some here and now and some hand-wavy future. So let me tell you where the dividing line was. The R scripts that were written and executed to create the heat map, those are standard R, doable in our product today. The graphical tool that showed the flow is standard product and available in Azure today, called Azure Machine Learning Studio. The integration and the use of them together is not today-ware, that's near-future-ware. And the mobile application that displayed is how much of that is here and now-ware versus upcoming-ware? little bit. So you saw a little bit of where we're going. The purpose of showing that demo was not to tell you we have something we don't, but to tell you that this is where we're headed. And this is the types of applications, whether it's the health of a jet engine or the health of a human, that we think we're going. Now, the question I always get, and I got it even this morning at 7 o'clock from a chemical manufacturer, when are you going to integrate with all my Microsoft products? And the answer is, watch this space. But let me give you a few hints. With the acquisition, we had begun a year and a half ago meeting with the SQL Server, HD Insights, and APS PDW teams to talk about what it takes to build capabilities that would allow Revolution Analytics to bring over our capabilities, including those 80-some highly parallelized applications. But then now that we're part of Microsoft, the stack got a whole lot more complicated. So you could imagine that we could implement integrations with SQL Server, HD Insights, Power BI, Azure Streaming, Visual Studio, of course. We will work all these plans out in coming months. Those of you that are working closely with your Microsoft team will have product briefings over time, as we always do, and we will be able to describe those. I personally think, and I'm no longer speaking as a Microsoft employee, so this is where the shepherd's crook comes and hauls me off. The most interesting part about becoming part of Microsoft leverages our ability to make analytics work on multiple platforms in exactly the same way, useful as a tool for deciding when you decide to split something up and put some of it in the cloud and some of it on-prem, how to do that easily. Imagine the simplest example there. What if all your big data is really flowing into the cloud because it's coming from sensors hidden in the engine control computers of your Toyota fleet? Well, that's probably data that we would call born in the cloud, and you probably want to leave it there. But the decisions about who to hand a spiff to among the customer base of who bought those Toyotas, you probably don't have that in the cloud. So that's an example of a place we may want to look at an architecture to create analytics and create predictive models by grinding that massive data in the cloud and then bringing those predictor equations or models down inside of the IT operations on-prem for the scoring of customers. Because we can instantiate a number of those different architectures, we bring flexibility to highlight one of the key values that we think Microsoft brings to the cloud business, and that means a hell of a lot of credibility outside the cloud. Microsoft has deep abilities on premises and rapidly growing abilities in the cloud. That sets the company up for doing a better job than most of fusing the on-prem investment and the cloud investment to create the hybrid cloud, so you kind of get the best of both. It's not going to happen tomorrow. It's not easy. But it's a lot easier when you have deep stacks on both sides as depicted in this chart, and you already have the integration between the layers at the data level, and you have commonality of the SQL dialects that you use on SQL Server, APS, and SQL for Azure. And then when you layer analytics atop that that is portable and transportable across those environments, suddenly those abstraction problems get a whole lot easier to deal with. So that's where I think we're going. Some of the next upcoming investments that are already in the process of being implemented. You saw some in the demo. The obvious ones will be to make Revolution Analytics available via Azure Marketplace. We will probably begin making some of the products available through your MSDN subscriptions. We will bind the products more closely with other related Azure machine learning capabilities, and we will certainly deliver versions of the product that allow you to use Revolution's massively parallel computational capabilities inside of SQL Server and inside of HD Insights. The order and the timing is something that we'll have to get back to you on. The SQL stuff is coming along well because we started that a year and a half ago. The HD Insights stuff will probably go pretty quickly because, after all, we already support Hadoop. This is just a new rev. So with that, I'm going to stop talking, and I've managed to leave 7 minutes and 59 seconds. That's a record for questions. Who has questions? Yes, go ahead over here.
Why did you prioritize those algorithms over others?
Most common use, available industry research that shows a mathematical technique for parallelizing them, and simple ability to do it. Some things are very hard. Some things are fundamentally, mathematically not tractable in a parallel environment. But for the most part, those are the very commonly used ones. There's some others we'd like to do, but there isn't available research to leverage to create them yet. Yes. That was the reactive, predictive, prescriptive. The question is, are there algorithms available in the set for predictive and prescriptive? It depends on how you describe prescriptive. For the predictive, yes. The modeling techniques, things like building GLMs and classifiers to then drive data into those GLMs, those are available today. That's typically what's in the set. Typically, the prescriptive requires some dose of domain knowledge, like what do you do to stop a problem from happening? If you've done it before, you can detect that with algorithms, but some of that is human knowledge that gets mixed in. Good question. I'd have to talk to you about your specific use case to talk about whether there's applicability there. More questions? Yes? The question is, how much of it will be available in SQL 16? I'm looking at Marcello because there's, of course, the always problem of, gee, if I say it now, will you hold me to it? The intention is all of it. The reality may vary a bit. We want to get a good body of that technology out as soon as we can, and that's what the team are working on. So I would actually answer your question with a watch this space and pester your account team to keep you hooked into that. We suspect that it will be part of the evaluation programs early on in the SQL v.next program. The team are working on it, so we've already built it before. We're hoisting up what we already did for Teradata and making that available, using that as the basis for SQL Server and then enhancing it significantly. So it's not like this is no clean sheet of paper. The algorithms already exist. We have a SQL-like framework, a little bit of melding and merging, and I think we'll be there. So there's a very good chance you'll see most of it in SQL 16, plus some new things that we always wanted to do. We couldn't do because we didn't have enough engineers. We now have not an abundance of engineers, but certainly a more stable business platform from which to operate. More questions? Netezza? Probably not. We have supported Netezza. I'm ex-Netezza, by the way. We have supported Netezza. We have users using our products with Netezza. Netezza offers, IBM, through the INZA libraries, offer their own in-database algorithms, and so they compete with us. So it makes it kind of difficult to go there. The R interpreter that we sell and the one we give away will both work just fine with Netezza, but you'll be making calls to INZA libraries as opposed to our scale R. Same sets of functions, probably worked off the same academic research papers to figure out how to parallelize k-means clustering. Techniques will be very similar. Calling strings may be a little different. And by the way, the scientist you saw in the demo who did the genomics demo, that guy in the back, chief scientist from Netezza. So we're very familiar with that. But we can talk offline if you like. Other questions? Yes, way in the back.
Are you planning to integrate with Microsoft or Skype for Business?
I'm sorry?
Skype for Business? Because they're going to be producing a fair amount of data.
Don't know yet. There are a lot of properties in the Microsoft family that produce lots of data, not the least of which Office 365. And Bing, and a lot of the work that has been done in Microsoft to create Azure ML was done by those same scientists. As those teams merge, I suspect we will get into that business. The first steps will be to integrate with the obvious data platforms, HD Insight, Azure, Azure versions of that, Azure SQL, SQL Server, and probably APS PDW. The data platforms will probably come first. The tool integration will come in parallel, and then we'll start looking at the next properties, the next product beyond that. The answer is really don't know. That was a long I don't know. I apologize. More questions? Thank you all for your patience.